My name is Anna Steffi, and we are Group 19.
My name is Zach Barnett, and I'm part of Group 19.
My name is Alana Jadwalis, and I'm also in Group 19.
I'm Zonglin Jia in Group 19.
And this is for our recitation 7. All right, and this is our joint document we've had together and we've been working on. So for problem 1 of this recitation, we have these 2 discs. One is more massive than the other, and we have a student talking about how the less massive disc is moving faster. When it crosses the finish line, the faster speed compensates for the lower mass. So each disc has the same momentum. And what did everyone else think about discs having either the same or different momentums?
I thought the momentum would be equal. That was my perception, because I mean, mass shouldn't really affect anything that has to do with momentum, because it's just the force net times the time it takes to apply that force.
I disagreed because, well, so the change in momentum would be just like the mass times the final velocity. And because the smaller disk crosses in like less time, as like the time goes down, then so would the final momentum. Like on the momentum is equal to F net times the change in time. So the larger disk would have more momentum because it has like a greater time. So it would be multiplying the force by a greater number.
Yeah, I had something similar to that. I wrote down because the force must act on the larger disk for a longer period of time to pass the finish line, the momentum will be larger. And I have like this all written out like in my little thing about time as well, making momentum larger. And in general, I just larger things with larger momentums. With masses or have like larger momentums. Gia, what did you get?
I don't agree with the statement, but I used the wrong formula. I think I counting. I'm counting like the coefficient of friction actually. So I'm not really sure.
I see.
I think I see where my misunderstanding kind of came in. It's a little silly now that I think about it, but I was thinking that they applied the force for the same amount of time and just kind of let the blocks slide. That was my understanding of it. So I was thinking that the change in time was the same for both, but I see now that they're pushing it the entire way across the ice. I see that, so it makes sense.
Okay. So part 2, apply the momentum principle to the situation in ways that allow you to determine the speed of each disk as it crosses the finish line and the time it took for each disk to get there. And here I'm really sure that everybody got really similar results. This was your setup, which is what I used to up here. It's the same idea. And then Alana's values also match mine. So I was pretty sure that all of us just really agreed on that.
Yeah, because it was just manipulating the equation.
And then when asked which disk has more kinetic energy when it crosses the finish line, one student says the less massive disk is moving faster when it crosses the line. Since kinetic energy depends on the speed squared, that more than compensates for the disk's lower mass. So it has more kinetic energy than the more massive one. What did everyone think of this one?
See, my answer is kind of invalid now because I was going off my previous result where momentum was equal. So I I can't really give much input here.
I disagreed because wouldn't they have, since they have equal force and equal distance, wouldn't that make their work equal?
Yeah.
I'm not sure if that's right.
I can just go into here. So that was disagree. The kinetic energy of each disk, delta EK, is equal because the energy of the system equals work, where work is the change in our distance plus force, and the force and the distance are both equal. So, and since the work is both equal, then that would have to mean that the kinetic energy is equal. There would be nothing else to make it unequal. So yeah.
That makes sense.
And then part 4, the last part of this question. Apply the energy principle to the situation in ways that allow you to determine the speed of each disk as it crosses the finish line. They should agree with the speeds you predicted in part 2. And I'll go first. To calculate with energy was a lot easier. I just did the energy is equal to the work. The work is equal to force times distance. And the kinetic energy is just 1/2 mass times speed squared. And then you could, and since we're just looking for, in part 4, we're just looking for the speed. You could just set those equal to each other, solve for that v squared for each v. That was really simple. And I
Yeah,
think
I agree with that a lot. I made it way harder than I needed to for myself, but I mean,
you brought gamma in here.
I really did. I don't know why I did that. I mean, I guess it would still work. It just would take longer to do.
Yeah. Okay. And yeah, we have the same answer. Last one, problem 2, part 1. What is the mass of the deuterium? Assume that you can neglect the small kinetic energy of the recoiling deuterium. And I think everybody got the same answers on this one. That is 3.34.
I'm actually going to ask if we are going to take account of the gamma ray, like the high energy photon in this question.
Yes.
Okay.
Yeah, because of that, because mass and energy are related and energy is being released, to find the mass of the deuterium, it would not be necessarily the sum of the just the neutron and proton combined, because energy was released.
Yeah. Okay.
Yeah. And so that's why you did use this equation, which was just an expanded equation of delta E equals work, where work is nothing. And momentum must be conserved, so the deuterium must recoil with momentum equal and opposite to the momentum of the gamma ray. Calculate the approximate kinetic energy of the recoiling deuterium and show it is indeed small compared to the energy of the gamma ray. Yeah, I had the same E, and this equation is the one that I use to relate momentum and energy. I think that was in our notes maybe. And I just put in like, yeah. the energy that we'd found divided by the speed of light. And then you could put that over here. Did anyone get a different answer for this one?
I think we're all right.
Awesome. Okay, that works out.